Raspberry Pi has released the Compute Module 4. It has many of the same specifications as the Raspberry Pi 4, but instead of breaking out connectors and headers on the sides, it gives you two Hirose connectors underneath that give you the GPIO and access to high-speed buses. This is really meant for industrial and professional use cases, and while you can buy a Raspberry Pi official I/O board that breaks everything out for you, I think it would be more fun to make my own using KiCad. And over the next couple of episodes, I'm going to do just that and show you how to get started to create your own carrier board. Let's get started. Example KiCad files for the Compute Module 4 actually don't run on KiCad 4 or 5. You need KiCad 6. At the time that this video was made, KiCad 6 was not out. So what we need to do is head to KiCad.org, go to Download, pick your operating system, and if this says current version 6 or greater, go ahead and download that. But for my purposes, I need to use the nightly build. So click on the nightly link, and then find the most up-to-date nightly build. So for me, that is November 10th, and we're going to do the 64-bit version. Let that download. When that's done, go ahead and run the executable, which should install KiCad for you. You'll want to do this and accept all of the defaults. While that's going, look for the Raspberry Pi Compute Module, and what we're looking for is the I/O board. Look for the product page on Raspberry Pi. You should see the I/O board, and what we're looking for here are the KiCad files. Let's download those, because we can use these as a template or as a way to give us some indication about how to lay things out. Finally, head to my GitHub repo for the carrier template, and let's download that as well. Go ahead and unzip all of these. Let's move both of these projects to the KiCad project directory. If you don't see it yet, create one in Documents or wait until KiCad has finished installing. Once KiCad is done, go ahead and open it. You should get to the Projects page, and let's start by opening the I/O board project. So that goes to Documents, KiCad, CM4 I/O KiCad, and look for the PRO file. I'm going to go ahead and enable acceleration, and this is the schematic for the I/O board. Notice that the I/O board uses hierarchical sheets in KiCad. You can double-click on the sheet to view the individual components in that sheet. Right-click and say Leave Sheet, or press Alt-Backspace to go out. Feel free to look through this schematic to see how the Raspberry Pi Foundation created the I/O board. The next thing I'm going to do is modify the template that we downloaded to be the new project. Feel free to start your own Git repo or clone it or do whatever you want and modify the carrier template and check it into your own repository somewhere. But for now, I'm just going to keep everything in the KiCad projects directory. So let's go into here. I'm going to grab the hardware folder. The rest of this is not needed for the project, and I'm going to paste it in the top level folder of the KiCad projects directory. Feel free to go ahead and delete the rest of the folders from the repo. I'm also going to rename this to whatever I want to call my individual project. I'm going to call mine the base carrier. This is a bit of a throwback to my old SparkFun days when I helped create some of the original blocks that you could put the Edison on. The base block was actually one of the most popular ones, and it was just a simple 2 USB connectors that gave it power, and the other one could be used for data transferring in and out. I think it was on the go, but I don't quite remember. We're going to keep our project here simple and use it just as a USB client, so hopefully we can talk to it from a computer, but we'll see how that goes. This is all experimental, since I don't actually have a Compute Module 4 on hand yet. The other thing you'll need to do is go in and rename basically anywhere you see carrier template, rename that to your project name. So these are hierarchical sheets that we will go into and modify later, but for now, any of these files that have carrier template, you'll need to rename them. So now what I like to do is open up another instance of KiCad. It will yell at us saying, KiCad is already running. I'm going to say, yes, continue. This actually opens up a second instance running on my computer, and that way I can flip back and forth between the CM4 I/O board schematic and Alt-Tab to the one that I'm working on now. So let's go to Open Project. We're going to get out of the GitHub repo, go into the KiCad projects directory, and go into the new project that we just created. Open up the PRO file, and this is our project. So open up the schematic. I'm going to enable acceleration, and as you can see, I created the template to look somewhat like the I/O board. So you can double click on these schematics, and I left you a lot of space here to create your own schematics, and you can even create your own hierarchical sheets outside of this if you wish. We won't need that for ours, but know that you can create them out here and link them all together. So the first thing you should do is click on the page settings and rename this. I'm going to update it with the current date, leave it at version 1. Since it is me, I'm going to leave the rest of these the same. Say OK, double click, go into each hierarchical sheet and do the same thing. Let's take a quick moment to talk about hierarchical sheets. To create one, there's a button on the right side that says Add Hierarchical Sheet. Click it, and then you can drag to create something that's like a schematic symbol. I'm going to name it Test, since we're going to delete this in a minute. And notice that it creates a new file on your computer that is basically another schematic. Hit Escape, and then double click to go in it. Once we're in here, I'm going to add a component. If you get this error, I'm not really worried about it. I'm not using any valves. And then we want to copy default global footprint library table. Say OK, and you should see all of the libraries here. I'm going to look for a basic resistor, add this to the sheet. In fact, let's add one more. Notice that there are a couple of labels you can use to connect things together. I'm going to hit W and create a couple of nets here so you can see what's going on. First, there are global labels. Control H to add them, so click on your line, name it whatever you want. A global label is connected to everything in the hierarchy. So if I leave the sheet and go into here and I create another global label, those will be connected. Next is the local labels. Use the local label to create a local label on your node. This name, this net, only exists within this sheet. Then we have the hierarchical sheet labels. Let's add one of these. I'm going to call it Hi, because I don't feel like spelling hierarchical right now. If we leave the sheet and we click on our hierarchy sheet, you should see an option that says Import Sheet Pin, and then Hi will appear there. This will allow you to connect lines and nets to other hierarchical sheets or to maybe some other components you have on this top level sheet. Those are the three basic labels you can use for nets. And I left this last one blank so that I can show you how to use, say, a ground or a power symbol. If you use a ground or a power symbol, these act as global labels. So any of these GND or power symbols that you add will be connected to all of the others in the other sheets. I hope that gives you a basic introduction to hierarchical sheets. We can leave these, and I'm going to go ahead and delete that one since we don't need it any longer. But note that if you want to create your own for your own project, you can do that. You can connect them, use global labels, or just use local labels within that. For now, we're going to be working with just these two hierarchical sheets. Let's start in the GPIO section. To begin, we'll make a power section that feeds 5 volts to the Raspberry Pi compute module. Notice that the compute module takes 5 volts in and spits out 3 volts or 3.3 volts and 1.8 volts. After some digging, I found this USB-C connector. USB-C allows us to supply 3 amps across the lines, so this is a much better way to go than, say, like a USB micro connector or something. And it will save us space rather than using a big barrel jack. Looks like Digi-Key does not have these in stock. Hopefully we can get a hold of these at some point. But for now, let's start by downloading the SnapEDA symbol and footprint for KiCad. Once that's downloaded, unzip it, and we can see that there is a KiCad mod file. This is the footprint, which needs to go into a library. To create a library, just create a folder with the suffix .pretty, and I'm going to give it the name of the part. So we'll just call it USB 4105-GF-A. I'm going to move the mod file in there. The step file is for the 3D viewer, which I don't particularly care about. So what I'm going to do is create a folder for the library that we can just drop into our user libraries. And I'm going to give it the same name as the part. And I'm going to move the .lib and the .pretty file and folder in there. Then let's cut that. We're going to go into our project, and there should be a libraries folder that was automatically created as part of the template. You'll see some of the files from the Compute Module 4 I/O board that I've included in there for the template that you can use if you so desire. But for this particular component, I'm going to paste this in there. Let's go back to KiCad. Here's our base carrier, and what you want to do, base carrier, bring up the project viewer, go to Preferences, Manage Symbol Libraries, go to Project Specific Libraries, and you'll see the CM4 I/O library already added. Let's click Add Existing Library. KiCad base carrier. Go up one and go to Libraries. Here's the library that we created, and we want the .lib file that is for the schematic symbols. Click OK, and I keep getting this error. It looks like it's looking for a legacy library. I don't need valve, so I'll just click OK for that. In fact, if I want to get rid of that, I can go find valve. I'm not using these, and then just get rid of that. Hopefully that will solve that error. We want to do the same thing for the footprint. So Preferences, Manage Footprint Libraries, Project Specific Libraries, and it should be the same steps. But this time, we're going to add the .pretty folder. Click OK. Let's add a symbol. We're going to add it about here. Here is the library that we just added, and this is the symbol for the USB-C connector. Anytime I add a custom symbol like this, I like to update the property values to include the manufacturer part number, as well as wherever I'm going to buy it from. So in this case, the Digi-Key part number. So this looks like the manufacturer part number, but I'm going to start over for some of these because you'll find that these names all are different. And when you go to create the BOM, it'll be on different rows and kind of a pain in the butt to update them to make them all one row. So I'm actually going to get rid of all of these. Let's bring up the Digi-Key page, and Digi-Key should have them all listed here. So the manufacturer is GCT, so I'm just going to copy that. I'm going to add a new field called manufacturer, paste that in, new field, MPN, which is the manufacturer part number, which should be listed here. New field. I'm going to call it the Digi-Key part number. And I'm going to use cut tape. That works well for single items. And the last thing we need to do is update the footprint. This should automatically point to the .pretty. This definitely does not look right. We created that in the USB 4105.pretty, and you should have the footprint here. Feel free to take a look at this. This should look like a USB-C connector, and double click on it. There we go. Footprint has been added. Okay. Something that I'd like to point out is that the Raspberry Pi 4 uses a USB-C connector for power. However, notice that after a whole bunch of research online, it does not appear that they connected the CC lines correctly, so we're going to do this a little differently. That being said, they do have an overvoltage protection diode here, which we'll use. In fact, we're going to use basically this same one. I found it on Digi-Key here. This works, and looks like they have an Ultra Librarian model. That makes things really easy in KiCad. Click download, KiCad. We want the KiCad model, download, log in. After you've logged in, you should be able to go to KiCad. You have to do the process over again. I'm going to be a rebel and do everything in millimeters for the footprint. That is because I'm going to copy what the Raspberry Pi 4 and the Compute Module 4 I/O board have done, and everything is laid out in metric. So you know what? I'm going to try a board in metric this time. From here, the process is kind of the same, just like we did with SnapEDA. You want to extract it, and it looks like everything is given the current date that you downloaded it. To fix that, I'm going to give it the manufacturer part number, which is just the same that's on the footprint right here. I'm going to update the schematic library. And footprints.pretty is super generic, which might mess up your libraries if you have more than one of these. If you have a whole bunch of footprints.pretty, it's going to look really weird in your library browser. So I'm going to give it a new name. There. That should work for us. In fact, I'm going to give this the same name, and we are going to cut that, and we're going to move it into our libraries. And just like we did before, go to project-specific libraries, and add the diodes symbol library, and do the same for the footprint. Rather than bore you with adding every component, I'm going to skip to the end schematic. Note that this process was the same for each component that I added. I found what I wanted on Digi-Key and downloaded a pre-made symbol and footprint library. Please see my other Intro to KiCad videos if you'd like a more detailed step-by-step walkthrough on how to make a schematic and footprint. As you can see, I added a few LEDs here. These match up with the CM4 I/O board. In fact, I directly copied and pasted these LEDs from this schematic and changed them to match the Digi-Key parts that I wanted to add. This is the USB-C section that we added in the first part. I added two 5.1 k ohm resistors to the CC lines. This will allow us to pull up to 3 amps. Notice that I left all of the data lines unconnected. I also added a GPIO port. These break out the UART, SPI, and NBoot lines that you can also find on the Raspberry Pi 4 header. The NBoot line needs to be connected to ground in order to upload an OS to the Raspberry Pi if you got the one with the eMMC option. Notice that I don't have an SD card slot here, which means that the CM4 module you buy must be the one with the eMMC. This board that I'm making will not support the light version. Over here, I added a Qwiic or Stemma port that allows me to connect a number of I2C sensors to my breakout board, and I've added some optional pull-up resistors here in case I want to put the pull-ups on the board itself. I put DNP for do not place, and that will tell me to just leave them as footprints and don't actually populate those parts. Down below, I added an EEPROM write protect jumper, so you can solder this if you don't want your end users to be changing the EEPROM on the compute module. Let's leave this sheet and go to the high-speed section. All I added here was a basic USB micro or on-the-go cable, but in reality it's just going to be a USB micro footprint, just like ones you find on many electronics nowadays, before we move to USB-C. However, here it is configured such that the compute module is to be used as a USB client. I'm purposely removing the on-the-go ability because I don't particularly want to figure out how to make it a host. I don't care to bring USB devices to this at this point. However, what I'm hoping to do is that I can just plug in a cable and I can get a serial terminal to my Raspberry Pi. To do that, I'm connecting the VBus pin to the ID pin on the compute module through a voltage divider. This was the same that was in the CM4 I/O board. If you go to the USB hub section, you can see that their on-the-go connector here connects through a 2.2 k ohm resistor to the OTG, which goes to the ID pin, and then another 2.2 k to ground. My understanding is that this pin allows this USB mux to select between USB client and the USB host, which is done through this hub, and then there's two USB connectors on the I/O board. But we just want to bring the client. I'm going to ignore the whole host section right now in order to keep the board simple. Part of that USB section was also an ESD suppression circuit, so I added one of these, which I found on Digi-Key. I hope this works. I have not had a chance to test USB on the CM4 because I don't have a CM4, and I pray when I get one and get the board, all of this works. Now that the schematic is done, we want to fill in the reference designators. So from any sheet in your schematic, just click the Annotate Schematic button, click Annotate, it will complete, and you should notice that the reference designators have all been numbered, regardless of which sheet you go to. From there, you're welcome to perform the electrical rules check. However, what I have noticed, if I run it, I get tons of errors. If I go into one of my sheets, all of my non-connected pins are going to throw an error. Some of the inputs and outputs, which look okay to me, I'm going to go ahead and ignore this for now. I can double check my schematic to make sure it looks good. Personally, I don't have a lot of luck with ERCs. I know that I'm probably supposed to care about them, but I'm just going to go ahead and delete the markers and hope everything works. It can always help to have somebody else look at the schematic for you and do a review prior to laying out the board or even shipping it off to production. Then we want to go to assigning footprints to schematic symbols. So click on that button. If I did everything right while I was placing down symbols and updating the footprints in those symbol properties, all of these should be populated. In fact, I can go in here and check by clicking on one of the footprints, clicking on the footprint viewer. Yes, that looks like my SMD diode. Those look okay. You just want to go through here and make sure all of these have an assigned footprint. If not, you can click on one. Say this one didn't have a footprint assigned. Find the footprint library, which this would be resistor SMD. Find the footprint you want to use, so the 0603, and double click on it to assign it. And you would do that for all of these if they were missing some of the footprints. All of this looks okay, so I'm going to click Apply, Save Schematic, and Continue. Click OK. I'm going to wait to do the bill of materials when I'm done with the layout. Click on the Open PCB New button, and you'll be presented with the template file. From here, click the button to update PCB with changes made in schematic. Click Update PCB, and close. You should get all of the components on your mouse. So just click anywhere to drop those. And on the next episode, we're going to take a look at placing them, routing them, and then shipping this board off for production. If you'd like to use these files for your own board or use it as a demonstration to make something similar, you can head to my GitHub repository, which is named RPi CM4 Base Carrier. And I will be keeping this project in here for now if you want to download it and make it yourself or modify it to your own ends. I hope this has given you a head start in creating your own carrier board for the Compute Module 4. Since I don't have a CM4 on hand right now to be able to test any of this, I'm just kind of hoping it works. So if you see something that looks a little off in the schematic, please let me know in the comments. I hope I'll get a chance to update everything prior to sending it out to production. On the next episode, I'm going to show you how to do layout with all of this and order all of the parts. See you then.